Hi, my name is Seyed from EDD Academy, and today I'm going to be covering verifying solutions to differential equations from Unit 7. Okay, so first, how do we verify solutions to differential equations? Very simple. We essentially just plug in the function into the equation. So in algebra, in order to see if a certain number satisfies a algebraic expression, we just plug it in where x was or whatever the variable was. Exact same thing in calculus and differential equations, you just plug in that function. So here's a very basic example. So let's say we have dy dx is equal to a constant c. Very simple to solve. It's just a basic linear equation. Y is equal to cx plus a constant of integration, big C. So we just plug that in where y was. And since this is a linear equation, we can obviously tell that the derivative will just be the slope of the expression, which is c. And this is a very valid equation, and it's a valid solution. So the best way to learn this is through some practice problems. So here's a very simple example. Show that y is equal to 5 times e to the 3x is or isn't a solution to dy dx is equal to 3y. Pause this video first and try it yourself. I'll wait for a few I'll wait a few seconds. Alright, now that you're back, let's get to the answer. So y is equal to 5 times e to the 3x is equal to e to the ln of 5 times e to the 3x. And using our exponential properties, we can merge that in. You'll see why we want to merge this in later. Okay, now we plug it in. And when we differentiate it, we can use the chain rule, as you'll see in the next section. So d du of e du times du dx will give us the derivative of the original expression. U in this case is 3x plus ln of 5. Okay, and since d du of e to the u will just be e to the u, we get e to the 3x plus ln of 5, and du dx is just 3. Since it's a linear equation, we get 3 times e to the 3x plus ln of 5. Now, the expression says 3 times y is equal to dy dx, and this satisfies that equation. On a side note, if we had decided to differentiate the original expression 5 times e to the 3x, we would have gone 15 times y as the other side of the equation. Now, you might say 15 times y and 3 times y aren't equivalent, but actually, in this case, you can make them equivalent. How you do that is by doing the process we did at the very beginning in reverse, by taking the ln of 5 out of the exponent spot and bringing it down to the front. And you'll get an extra factor of 5, and 5 times 3 is 15. Here's another practice problem. Is y is equal to e to the negative 1 over 2x squared a solution to the following differential equation? X cubed times dy dx is equal to y. Pause this video and try this yourself. Okay, hopefully you've tried it by now, and let's get to the answer. Okay. So first, let's differentiate this. Very simple step. Well, in this case, not very simple, but still. So dy dx is equal to d dx of e to the minus 1 over 2x squared. We can use the chain rule again. So d du of e to the u is still e to the u, where u is minus 1 over 2x squared. And du dx with simple power rule manipulation, you get 1 over x cubed. Plug this into the original equation, and x cubed times 1 over x cubed is just 1, so we end up with the original expression, and this satisfies the differential equation. Here is a slightly more complicated differential equation, or solution to a differential equation. So show that this y of x is equal to the integral from 0 to x squared of e to the power of t dt is a solution to dy dx is equal to 2y of x times the square root of the natural log y of x. Now, that's a pretty complicated expression, but it's actually pretty simple once you get down to it. Alright, so first, we're going to take the derivative of this expression. Okay, so we're going to first start by doing a little bit of substitution. U is equal to x squared, right? So we're just going to do a little variable swap for, I guess, simplicity. Okay, now according to the second part of the fundamental theorem of calculus, we know that if we differentiate an integral from some value to another, it'll just be the original expression with the limits of integration in it times the derivative of the limits of integration. So du dx times e to the power of u, okay? And since we know what u is, right, we can just get to the last step, and that'll be 2x times e to the x squared is equal to dy dx. Okay, now we just have to work on the right hand side, and we get, if we plug in with the value for y, we get 2 times e to the x squared is times the square root of the natural log of e to the power of x squared. And through some simplification, we can see that these two sides are in fact equivalent. Alright, for our final example, we'll verify that y is equal to sine of x is a solution to the following. dy dx is equal to the square root of 1 minus y squared. Pause the video and try this yourself. Okay, so first, we're going to calculate the derivative of y. So the derivative of sine is obviously cosine. Now, let's use some Pythagorean identities here. See that cosine x is equal to the square root of 1 minus sine squared x. You should probably recognize that these are true, but if in case you don't, Pythagorean identity, and cosine of x is equal to cosine of x. Since cosine squared of x plus sine squared of x is equal to 1, and by solving it for cosine of x, we get square root of 1 minus sine squared x.